Okay, so I'm going to try to talk about this with as much clarity as I possibly can, but don't worry too much if it's not all clear today. But we use the term exponential, and usually when we say exponential, what follows that? Someone talks about exponential increase or growth. All right, that's typically what we say. We can also talk about exponential decrease or decay. Okay, both those things are issues, and both those things are things that we need to be aware of. But we might think that x squared or x cubed, we might think that that's exponential, but it's not. Okay, these things grow at a pretty good rate. So that's all right. These things grow at a pretty good rate, but that rate is somewhat consistent. So even if you have x to the 300,000, that's quite a rate, but it's not exponential. Let me show you what's exponential. What's exponential is a to the x. Something raised to the x power, that grows at a completely different rate, a completely different level of growth, okay? So that if you're graphing something like this, now again, we know that x squared looks like that, right? You know, it looks like that. But a to the x, it kind of does this sort of thing. So that it's, and then goes boom like that. Okay? It just rockets up. Provided that that is for a greater than 1. Any a greater than 1. Okay? And it doesn't have to be much greater than 1. But any a greater than 1 will do that. So the interesting thing then is what happens, to me what's equally fascinating is what happens if a is just less than 1. So let's suppose, so that's an estimation of the graph of 1.1 to the x. It looks about like that, okay? What if we had instead, get another color here. What do you think 0.9 to the x would look like? So the difference between 1.1 and 0.9 is 2/10. 2/10 of 1. Or 2/10 is 2 of 2/10, 1/5. What does the graph look like? Any idea? It's okay if you don't know, by the way. It's not surprising. Here's the thing. That graph looks like that. So when you're talking about exponential, your base changes by 1/5. All right, 2 dimes, 20 cents, right? 1/5 is your base and change, or your change in base, excuse me. And it goes from something that grows and gets big really fast to something that gets tiny really fast and never gets big again. Okay? Now, this is just conceptual stuff. Trying to see conceptually what is happening with this sort of a function. But, we will deal with this beyond conceptually. We'll deal with it. We'll have to do the math. We'll have to do some work with it. So, this is the right page here, sorry. An exponential function then is of the form f of x equals a to the x. And as we said, this black graph is the graph for any a that is less than, any a that is greater than 1. Okay? Now, if a is between 0 and 1, this is the graph. Now the question is, can this change? Can your function change? Yeah. So let's suppose that so a is a constant, right? So if you add something to it, it's going to shift, right? So you can do things to it. You can shift it. You can divide it and change it a little bit, but ultimately it's going to look like that. Okay, and then again from 0 to 1 look like this. Now you get a less than 0, and then you've got a whole different ball game, right? We're not even going to deal with that right now. But a less than 0 is going to change things a lot, because so when a is less than 0, then we care about whether the x is even or odd, right? It becomes really messy. So it might be solvable, but so we're just dealing with positive a's between 0 and 1 and greater than 1. That's all we're dealing with right now. So in order to be able to function well with these, in order to be able to do the math of these, you got to remember some things that you learned way back when. Should have learned them back in pre-algebra, okay? So some things like a to the s times a to the t equals a to the s plus t, right? Okay, so that is, if you multiply the same base with different exponents, you just add the exponents. If you have a to the s and you raise the entire thing, the base and the exponent to the exponent, well, in that case, you multiply them. It's a to the st. If you have a quantity inside a parentheses, well, that equals a to the s, b to the s. Now, again, these are things that you ought to know. So this should all be review. If it's not, I'm sure it's review, but if you haven't trouble remembering it, that's okay. But let me ask you this question. Is this the same as that? It's not. That's important. Recognize that the exponent only applies to the variable there. But if you do that, then it's 3 squared x squared, which of course equals 9x squared. If you do that. So just reminders. For the exponent to be applied to a quantity, it has to be outside of some parentheses or something. Okay, it can't be just, this coefficient is not tied there if you don't have parentheses. So those are not the same. So what else do we need to know? This is one you should know. 1 to any power is 1. Helpful thing. How about a to the negative s? Well, a to the negative s is 1 over a to the s. By the way, these are the letters that they chose. And after saying that, it sounds weird. Anyway. What about, this is not in your book, but a over b to the t equals a to the t over b to the t, right? Or if you have a to the t over a to the s equals a to the t minus s. So these are things that you should know. And then one more important one that you should know. Everyone know a to the 0 is what? 1. Anything raised to 0 power is 1. That's another one of those things that if you were a theoretical mathematician, you could probably tell us why. I don't know why a to the 0 is 1, but it is. And it works for us. It works for us everywhere. And I would argue, I think you could argue that God in his infinite wisdom has made that work mathematically, because it does. Even if we can't understand it. All right. So those are all your laws of exponents that you've got to know. You have to know what exponential function is. Now, when we think about an exponential function, okay, as I said, the graph looks something like this. Black for a greater than 1, blue for a between 0 and 1. Those are what the functions look like. On an exponential function, and these are things that are in your book, but you're going to want to know them, and it saves you a great deal of trouble to know this. For an exponential function, the x-axis is the horizontal asymptote. And there is no vertical asymptote. Okay, so even though it keeps going like this, usually when you see something like that, you'd like to say, well, there's a vertical asymptote, but there's not. It just keeps growing. And there's no limits. There's nothing that x can't be. Okay? Right? If you look at a of x, we're going to go back to this function. Is there any x that doesn't work? Well, there's the x. But is there any x that you can't use? There's not. The domain is negative infinity to infinity. Every value for x works on an exponential function. Every possible value for x works for the domain. Now the range, if the range is 0 to infinity, the x-axis is an asymptote, and you cannot get less than 0 if a is positive. Now, why is that? So let's think about. So again, I know that probably none of you are setting out to teach the philosophy of mathematics, but why is it that it doesn't matter what x is, this quantity is always going to be positive? Let's what's that?
Because the negative times the negative equals a positive.
First of all, we're dealing only with a greater than 1 at this point, okay? Or a greater than 0, but right now we're with a greater than 1. So that way we don't actually get it. If a is less than 0, we have a whole nother ball of wax to deal with. But if a is greater than 1, let's suppose that x equals negative 100. Well, that's just, so that solution then is just 1 over a to the 100. As long as a is positive, it doesn't matter if x is negative, it's always going to be positive. And x could get really, really small, like negative 500 billion. And that would be a really, really small number, but it's never going to be negative. Okay? So this is why we talk about, that's why it's typically described as exponential growth, although the growth can be a decay, and we'll talk about that later. So, all right. And if you graph it, you'll find that. If you graph this, you'll find this is what it looks like. It never gets below the x-axis. Your solution, your f of x is never, your output is never negative. It's always positive with an exponential, provided that your a is greater than 0 and less than 1 or greater than 1. So please, we're out for a minute. So this blue is for f of x equals a to the x, comma, 0 less than x less than 1. The black, same function, a to the x, comma, x greater than 1. So we'll talk later, we'll apply this to finances later, which is great fun. But look at the difference, okay? So let's suppose, so if we're going to look at this, if this one, our A is 1.1 to the X, that's this one. And this one, our A is 0.9 to the X. Now let's think about that financially. So basically what we're saying is, if you could grow your finances by, if your finances are going to grow by 10%, and they're going to grow exponentially, okay. But if you're at 1.1, that's a 10% change. The potential for growth up is super high, and money does actually grow fast like that. And again, it grows fast provided that it keeps growing. So this is a rudimentary illustration because the market changes, various things change. But in the same way, if you are losing money every year, so you're at 0.9 of what you you also can quickly use it all. Yeah.
So it's like the first one, because like it keeps adding 10% on top of it, like so it adds 10% and then it adds 10% of the total, including the last 10%.
Yes, that's what it does. So it's 1.1. You've got to the power of 1, but then you've got 1.1 to the power of 2, 1.1 to the power of 3. But you've got everything in between there too. It's not just 1s, 2s, 3s. That's what exponential growth does, and we'll see it again here in just a minute. So the objective today is to see these things conceptually the best we can. So, my phone is going crazy over here for some reason. I don't know why. What's happening? All right. So now we're going to take this another step and think about this. There are a lot of ways. There are a lot of different exponential functions, right? There are a lot of different ways you can do this. Your A can be all sorts of things raised to an x, and they're all exponential. So an exponential function is something, your a raised to an x, and a can be any number of things. But there's a pattern that can be seen in the world, and there's a professor or a teacher, I don't know, he probably is a college professor too, but on YouTube that I really like to watch. His name is Wu, and he gets so excited about these things, and so I'm sort of going to use his analogy. But when we're talking about value of money, okay? So you all have probably learned the simple interest equals principal times rate times time, right? You know that the interest earned or the interest owed is principal times rate times time. Do you guys know that from, you never learned that? Okay, well, good. Well, let's learn it. This will make this much more sense. So let's suppose that you borrow money, excuse me, not that, you save money, and you're getting an interest rate of 5%, which these days would be really, really good for a typical savings account. And you can get way better than that in mutual funds, but those are more risky. But let's say your interest, okay, is 5%. So it's 0.05, okay? That's a decimal 5%. And let's say you save $5,000, and you do it.
Can I have Chase Scott to the front office for dismissal, please? Chase Scott to the front office for dismissal.
For 3 years, okay? This is simple interest here, okay? So we do that for simple interest. So this is going to tell you how much your interest is, and if it's annual interest. So typically, our interest rate is annual interest. Yes.
There's gonna be more word problem stuff again.
Yes, there's going to be, unfortunately.
Oh, no.
But so right now, but this is just preparation for what we're going to do. So, if you did this, so 5,000 times 0.15. Use the wrong button. So this means after 3 years, you get $750. So interest equals $750. That's simple interest. That means that it's not compounded. That means that's simple interest. Now, that's not the way interest works. Okay? How does interest actually work? Well, they typically will compound it monthly, or actually your bank will likely even compound it daily. If you owe them money, I promise you they compound it daily. Okay? If you owe them money, they compound that interest daily. So you get a credit card and you buy a sweater for $25 at 28% interest. They're compounding that interest, even though it's an annual interest rate, they're compounding that every single day. Okay? This is simple interest. But compounded interest works in a different way. And using compounded interest, often we want to look, what we're really concerned about is not how much interest, but what's the future value of something. So our future value is often 1 plus 1 over r raised to the r. So that's an important formula for future value. Well, let me correct that. R times t, 1 over r times t, okay? Sorry. So 1 plus 1 over the rate times time raised to the rate times time. This will tell this, if you compound your interest You can do this over different different increments. So you can do it for, what if we do it for for every month over a year. So 12 times a year. Or you do it 10 times a year. Or maybe you could do it every day, 365 times a year. Daily, you do a variety of things. So each time you compound it, it's going to, however often you compound it, okay, so your compound another way to look at that compound is your n. You call that your number of, so n is the number of compounds. Now, you would think, well, if the more times I compound this, it's going to keep growing more and more. And that is somewhat true, but it has a limit. Okay? So, I want us to imagine we're going to imagine investing $1, and we're going to imagine that $1 gets a full 100% interest. Now, you might say, well, that seems unlikely. Well, in banking, it probably is unlikely, although some things can make that kind of profit. But again, using Mr. Wu's analogy, where do things actually increase? So for something to increase by 100%, that's a double, right? So let's suppose you had 2 rabbits in a cage. What are the chances those 2 rabbits will double? A male and female rabbit will double in a year. Really high. They'll go way more than double. But let's just assume that they are, less fertile rabbits. And so they're only going to double. Okay. So that means the increase in rabbits is going to be 100%. Okay. So when that happens, we end up with a function that looks like this. Okay. So if our n is going to relate to the amount of time, okay, after 1 year, right? So we're going to let, so n equals time. That's what, so there I had t because that's what we use in finances, but in books, when you're looking for number of increments in calculus books and pre-calculus books, they use n. But if you take accounting, they'll use t. Same thing though. So n equals time. So we're going to say, let's do this for 1 year. Or for one period of time, we'll call it a year. So 1. So then we plug 1 into there and we get 1 plus 1 over 1 raised to the 1. And that equals 1 plus 1 is 2, raised to 1, 2. Now let's do 2. Okay, 1 plus 1/2 raised to the 1 or raised to the 2. What's 1.5 squared? 1.5 squared. Do we know that? It's 2.25. Let's try 3. Well, now we're going to get 2.48. And something else. Here's the question. What if I do this for 1,000? Okay? So let's do it for 1,000. 1 plus 1 over 1,000 raised to the 1,000th power. Okay? Well, it's going to be 2.7169. Now, from 1 to 2, we have a little bit of an increase. 2 to 3, a little bit less of an increase. From 3 to 1,000, that's a surprisingly small amount of increase, right? Okay. And from 1,000 to a billion, it only changes to this. Is that 2.9, right? Oh, this is wrong. This is, no, 6, yeah, 2.18. 2.71828. Okay, so here's what we're saying. There comes a point when your compounding of things doesn't change the calculation. Okay? So, so if we write it like this, the limit as n reaches infinity of 1 plus 1 over n raised to the n. So we're saying we're going to let n get really, really big. Okay? And so big we can't define it. Infinity. And so if n gets so you are, if you notice here, you are compound, this is exponential, right? But that equals a value that we call e. Yes.
Can I answer that?
Sure. And what we're saying is that there is, E is called the exponential function. Now, this f of x equals a to the x, that is an exponential function. E is the exponential function. Okay? Like the Frankfurt Christian Academy. It's the exponential function. It's the one. Because we're saying that there is a value that tells you how much something, tells you the limit to how much something will change, no matter how many times you compound it. Now, again, this is not dealing with the issue of growth. Shoot. Sorry. No, I'm not interested. I'm calling back. Trying to get something for our church, but I'll call him back later. So this value, this 2.7, okay, that is not giving you the value of the function. That instead is telling you, again, it's telling you a standard by which you know that the function will change, right? Because we know the value of f of x, as long as a is greater than 1, it keeps going up, up and up and up and up. Nothing to stop it. So the 2.71828 has to do with how much it'll change. It has to do with probabilities. So I think this might come up in later chapters, but I think it may be more clear then. But if you're talking about a random probability of things happening, well, that random probability can be defined with the exponential function. So random probabilities are roughly 1 out of 2.718, again, with other factors involved in it. So, all right. And they are also impacted, they're impacted by other factors. So they give you an example of that on page 318 in your textbook. They say, let's evaluate. By the way, so this E you have on your calculator, right? It's a value. It's on your calculator. You don't have this. This E is like I, except the E is irrational. I is imaginary. E is a real number, but it's an irrational number. So you have E in your calculator. So, for example, they say, how can we determine? They give an example of you're a Burger King drive-through, and the cars come in at a rate of 12 cars per hour or 0.2 cars per minute. Okay, so 12 cars per hour. Not the Frankfurt Burger King, they closed. I'm disappointed.
Frankfurt had a Burger King?
What's that?
I didn't even know Frankfurt had a Burger King.
It was a catty corner over from Sonic.
Oh, okay.
Over there by Arby's, but it closed. All right, so 0.2 cars, 12 cars per hour, 0.2 cars per minute. So, statistics tells us that the probability that a car will show up in relationship to a particular time, like 9 p.m., is 1 minus e to the 0.2 t. So, and t being elapsed time. So if you start at 9 p.m., so 9:05 is 5 minutes, okay? So I guess it's letting us use. So yeah, the t is 5, so minutes. So f of 5 1 minus e 0.2 times 5. So it's 1 minus, is that e to the 1? Oh, sorry, it's negative 0.2. 1 minus e to the negative 0.2 times 5, which is going to be negative 1, right? So it's going to be 1 minus 1 over e, which you could do on your calculator.
Can I have Gracie Hartman to the front office for dismissal, please? Gracie Hartman to the front office for dismissal.
So, let's see if I can do that on my calculator quickly. It's roughly 63%. Okay, so again, this may not be important to you right now, but this E becomes the value that that determines many statistics or probabilities and determines the rate of growth and and decay of bacteria, of money, a variety of things. So 1 minus 1 over E like I said, is going to roughly be 0.63 approximately. So it's 63%. What they're saying is that if Burger King has 12 cars per hour on average during the day, then there is a 63% chance that in the first 5 minutes you'll see a car. From 9 to 9:05 that a car will show up. Now, again, that might not be super important. This becomes, it becomes a tool of calculation. So, all right. So let's try just a couple of these. Because we have to be able to do a couple different things. One of them is you can graph these on your calculator. The other thing that your textbook has you do, but I'm not going to have you do, is make sure you know how to type these things on your calculator. So if you want to take 3 raised to the 2.2, how do you do that? And then how do you approximate it with a calculator? So on my calculator, you'll have x to the y. And so you'll type in the x, press the x to the y, type in the y, which is the exponent, and you get the value. And I think you guys should have the same thing. Different position. Mine's just an iPhone, but you have a different position. So you need to be able to do that. Well, let's try to do just a couple things mathematically with with these exponential functions. All right. Yes. So on page 320, number 33. So 4x to the 7th. So this is your function. It's an exponential function. So 4 to the x equals 7. What does 4 to the negative 2x equal? So how do we figure that out? So the best way to do that is to start with 4 to the x equals 7. And you got to figure out a way to manipulate it to end up with 4 to the negative 2x. If we take both sides and raise them to the negative 2, we'll get 4 to the negative 2x, and that equals 1 over 7 squared, which equals 1 over 49. So you have to be able to do algebra now using all of these rules of exponents that up till now you've basically only done arithmetic with. I don't remember, my Algebra 2 class doesn't do much of this. They do learn about logarithms, they do a little bit maybe, but not a lot. So let's try another one. Let's try 35. Okay, so 35. 3 to the x, is that what it is? 3 to the negative x equals 2 what does 3 to the 2x equal? So how are we going to take 3 to the negative x? And how are we going to get that to be 3 to the 2x? What's that?
Both sides to the negative 2.
So we just have to go -2, -2, and we're going to get 3 to the 2x, because negative x times -2 is 2x, to the -2, 1 over 2 squared, which equals 1/4. Right? Your ability to do the algebra with bases and exponents will determine your ability to do these types of problems. Okay. All right. So, I know, like I said, I know this is taxing stuff. I want us to try one of these, a couple of these word problems. If you all need to go, that's fine. But so I'm going to make a really short assignment, and then we're going to do 1 or 2 word problems together. So I haven't put this on Google Classroom yet, but okay. Okay, so 34 and 36. And then we'll do okay. Let's do, and then 40 and 42. So just those 4 problems, but let's do 40 together. Okay. So we're going to do 40 together, and then you guys can do 34, 36, and 42. So 40 is, this is the normal healing of wounds can be modeled by an exponential function. If A0, not A2 to 0, but A0 represents the original area of the wound, and if A equals the area of the wound after n days, then the formula so what are we saying is happening here? We're saying that the value E raised to negative 0.35 times the number of days will tell you how much of the wound is left. So remember when I talked about the future value and interest? Okay. This is your AN. This should be A0, sorry. This is your AN. This is your future value. So, and I don't know how, I don't know if all healing happens at this rate. But again, the The basis for the value E is the fact that this sort of thing occurs in nature. So naturally, this rate of healing is probably legitimate. And there will definitely be some rate. So if the original size of the wound is 100 centimeters, and that's probably 100 centimeters squared, but 100 centimeters squared. That's the original size of the wound. How big will the wound be after 3 days? And how big will the wound be after 10 days? So if we want to calculate that, and say A after 3 days is, so this is original, so that's A at 0 days. When did it happen? When your sibling smacked you, in the back with that, shovel, shard, that scraped glass. Yeah, I got bad quick. They can come in or you can go out.
No, we're gonna finish this problem.
Okay, well, I'll do this quickly. So, 100 times Z, the negative 0.35 to power of 3. That's your N. That's your solution, which you do almost entirely with your calculator. Okay, so you have to do the exponent first, right? I should get a real calculator instead of this. So you're going to have an e to the x. Okay? E to the x. But in my case, I've got to type in this value first. So it's going to be negative, 0.35 times 3 is 1.15, right?
Maybe. You're the one with the calculator.
Oh, I did that in my head, but that's just, what's that?
1.05.
1.05, thank you. All clear, negative 1.05. I did it wrong, see? And then I go e to the x, and I'm going to get so this value here is 0.3499377.
How did I get 1 without 0? I got 34.9.
Did you multiply the 100?
Yeah,
I didn't multiply the 100 yet.
okay.
You could. I didn't yet. So then it's going to be 34. Let's see, you got to do the exponent first for sure. 34.99. That means on the third day, it's only 35 centimeters instead of 100 centimeters. So now again, it depends on the type of wound we're talking, right?
Yeah.
Let's assume this is a shovel and it's a bruise. I would say if instead of being a shovel, it was a shard of glass and it was cut, probably just would heal slower. I'm sure there's a great Mythbusters show on that or something. But anyway. Now, what about the end of, it says then what about 10 days? So 10 days is just A10 equals 100E times 10. So that one's going to be easy. So negative 3.5 e to the x could be 100 times 0.030197, which equals times 100 is going to be 3.019. So 3 centimeters after 10 days.
Some fast healing.
Probably, but also, I hope you're gonna come to love this value E, because it's there all the time, it's already in your calculator. And that really, could you imagine trying to solve this in another way? Being told, well, the injury is going to reduce by this function or whatever. Well, what we're saying is that you don't need the other function. E is your function. E is your value. Okay? So that's just a few problems that you guys can work on. That means it leaves you with 3, 34, 36, and 42. Yes. Sure. All right.
Are you free?
Thanks for hanging in there, guys. This is tough. I know, but you're sticking in there well. All right.
Can you tell my grade report?
Oh, yeah, I think mine's.
Just set it right there. I'll sign it and I'll leave it there for you to pick up.
Okay.
Let me get off this first.
What is it right now?